Hello everyone, Mr. Lee here. In this video, we are going to be doing a angled forces problem. Alright, let's begin. So this problem says a 20 kilogram refrigerator is being pulled across the floor with a rope. The rope is being pulled in a downwards and rightward direction at an angle of 30 degrees with a force of 200 newtons. A frictional force of 20 newtons is felt by the refrigerator. Alright. We need to determine the acceleration of the refrigerator and the normal force of the refrigerator. So I have my scenario up here. I'm going to do a quick drawing of the current scenario. So let's do this. I'm going to draw my best impression of a refrigerator. Boom, look at that. That's a nice refrigerator if I ever saw one. Okay, so we have a refrigerator right there. We have a frictional force, so we know that's moving to the right because the rope is being pulled like this, right? So if that's the rope, let's just call that tension. Okay, the rope is pulling it down and to the right, and we have the force of friction going to the left because this object is moving to the right. All right, so those are all the forces according to the problem. Now we got to figure out the other forces that are involved that is implied and not given. So we have the normal force and we have the force of gravity. Okay. Notice I made the normal force a little bit bigger because, spoiler alert, the normal force will be greater than the weight of the object. All right, so this is my free body diagram. Now, if you watch the other video, you will know that if on the AP exam they ask for a free body diagram, this is what you have to submit. However, this doesn't help us at all when we are trying to do like the math behind it. So what I'm going to do is I'm going to create a component version. Okay, so I'm going to draw it on the actual free body diagram, but just so you know, these are not real forces. All right. So the first one, we're going to call that T sub x. Once again, not a real force. Not a real force. That's a component. And then we have, boom, that's going to be called T sub y. Okay. And we'll call this 90 degrees. And the problem didn't specify, and it usually does, but I'm going to call this 30 degrees. Okay. Let me do it in a different color so that we can see it a little bit easier. I'm going to call, let's do that. Ooh, orange. Yeah, this will be 30 degrees right there. Okay. All right. So this is my component version of the free body diagram. Okay. All right. Now, in order to solve this, let me just write down a couple of things. So we know that the mass of the fridge is 20 kilograms. Wow, that's not heavy at all. And we can figure out the force of friction, right? Yeah, they give it to us. The force of friction is 20 newtons. I just want to put that in just so that we know it. We know that the weight equation is mass times the acceleration due to gravity. And if mass is 20 and the acceleration due to gravity is 10, we have a weight of 200 newtons. Okay. All right. So we have the weight of 200 newtons. The force of friction is 20 newtons. To the left, so that'll be negative. And we have this broken up component version of this tension. All right. Now, if I want to specify what T sub x is and what T sub y is, let me show you what to do. So we know, let me do this in red for T sub x. Okay, so if we want to know what is T sub x, well, first we see that this is a right triangle and this is the angle right there. So if this is the angle, this red dotted line, that side is adjacent to this 30-degree angle. So if we're using SOHCAHTOA, we can see that the adjacent, we have to use cosine. Okay, so we have the cosine of theta is equal to adjacent over hypotenuse. And we can, clarify this a little bit more and say that the adjacent side is called Tx and the hypotenuse is just called T. And therefore we have Tx is equal to T cosine of theta. And we could do the same for Ty. Okay, so according to this angle right here, Ty is opposite of 30 degrees. And so opposite, we have to use the sine trig function. So sine of theta is, opposite over hypotenuse. and that will give us the sine of theta is equal to ty over t, and therefore that makes ty is equal to t sine theta. Now when you do enough of these, you'll pretty soon figure out that the shortcut is usually going to be the force of either x or y is equal to the hypotenuse times the trig function times the theta. Okay, so that's going to be the shortcut. But I like to just go through the steps when we first start off. All right, so the first one is asking for the acceleration of the refrigerator. Okay, so we got to imagine, is this refrigerator accelerating in the vertical or the horizontal direction? Is it accelerating in the y, aka the vertical, or the horizontal, the x? Now, my best guess is that it's accelerating along the x direction because it's being dragged along the x direction. So I need to create a net force formula for the x direction. So this is solving for A, right? I'm gonna zoom out there. The net force in the x direction is mass times the acceleration of the x. Yeah, and so we're going to use a technique that I described. I'm going to start at the 12 o'clock mark, which is the normal force. I'm going to go around the free body diagram to see all of the x forces. I'm going to ask myself, does this belong? Okay, does this normal force belong in the x-axis? It does not. Does this x tension belong to the x-axis? It does. It's pointing to the right, so I'm going to make that positive. What about this ty? Does that belong? It does not. What about this tension, this angle tension there? Does that belong? It does not. What about this weight, F of g? Does that belong? That does not. What about this force of friction? Does that belong? Yes, that does. Ding, 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 ding. All right, cool. So I put that as a negative because it's pointing to the left. It's equal to mass times the acceleration of the x. So A is asking for the acceleration of the refrigerator. So all we have to do is solve this in variable form, and we're going to divide both sides by the mass. So we get A sub x is equal to tx minus f of f divided by the mass. Okay, and at this point, well, let's clarify it. Let's clarify a little bit more. So we know that A sub x is equal to, we said t sub x, if we look down here, is t cosine theta, t cosine of theta, and when we don't know what that is just yet, so we have something like this. Okay, now we can put it in numbers. So A sub x is equal to the tension force is, what did it say? The tension force is, 200 degrees. 200 degrees, or excuse me, 200 newtons times cosine of 30 degrees minus the force of friction is 20. And the mass is 20. Okay, so if I were to plug that into the calculator, now let me show you what I like to do. I like to do this step by step. So here's my calculator, and the reason why I like to do it step by step is that way I know I'm not going to make mistakes. I'm going to do the trig function first. So first I want to make sure I'm in degree mode. You see, if you use Google, it automatically goes to radian mode, but we don't want that. We don't want that evil. So I'm going to go to degree mode, and we're going to do the cosine of 30. So I'm going to do 30 and then cosine. Crap. Ignore. All right, so I'm going to do cosine 30. Okay, enter. Times 200. Okay, so we get 173.205 minus 20 divided by 20. All right, so I did that individually. I didn't type that all into one line. And so we get an answer of, oh my gosh, I didn't catch that, 7.66 meters per second squared. And that positive 7.66 means that it's moving to the right, accelerating to the right, accelerating. It does not mean it's moving yet. It could have a velocity of 0. So it's just accelerating to the right. Like that. Yeah. Okay. So both of these answers would suffice on the AP exam. Usually on the AP exam, this would only give you about 1 point, whereas this, I'm going to say that gives you about 200 points. I made that number up, but it's a lot more than the actual answer. Cool. Now let's figure out the normal force. All right. So if we take a look at here, the normal force belongs in the y-axis. So I'm going to create a net force equation for the y-axis, like so. Okay, same strategy. I'm going to go to my free body diagram, the component version, and I'm going to ask myself, does this belong in the y equation? Does this normal force belong? Yes, yes it does. Good. F of n. What about this t sub x? Does that belong? That t sub x does not belong. What about this t sub y? This t sub y right there, does that belong? It does, and it's pointing downwards, so we get negative ty. What about this angle t? Does that belong? That does not. What about this weight equation, f of g? That does belong, because it's pointing down. We'll make that a negative. What about this f of f? Does that belong? That does not. That's in the x direction. So this becomes our equation. Yeah. Cool, cool, cool. Now, we see here, and we got to think about this logically. Is this refrigerator accelerating in the upwards or the downwards direction? No, it's just being dragged around left to right. So we can say that this acceleration is 0, and mass times 0 gives us 0. So our equation looks something like this. Cool. We are looking for the normal force, so we're going to solve this in variable form first. I'm going to move this ty over to the other side. So we get f of n is equal to, negative f of g, excuse me, plus ty. Okay, and we're going to move this weight equation, or that weight, over on the other side. So we get this normal force is ty plus f of g. Cool, cool. All right, and we are going to substitute in the equations. So we know that ty, if I see over here, we see that ty is t sine theta. So I'm going to write this of f of n is t sine theta. And we know that the weight equation is mass times the acceleration due to gravity. I'm going to box that, because that's going to give me, you guessed it, 30,000 points. Oh my gosh, 30,000 points right there for that answer. All right, but let's figure out a numerical answer. So we want f of n is equal to the tension, what was the tension? I believe it was 200, times the sine of 30, plus the mass. What was the mass of this object? The mass of the object was 20 kilograms. Okay, 20 kilograms times 10. Okay, so if we do that and we bring out our handy dandy, ever so trusty Google Scientific Calculator, I'm going to shift that over there. Clear that. Okay, so we get, I'm going to do this individually, the sine of 30, boop, times 200, boop, plus, parentheses, 20 times 10. And we get 300. Da, da, da. So our final answer is 300 newtons. Yeah, box that. All right, how many points should we give ourselves for this one? You guessed it, 1 point. Not as important. But I want you to see something here. Notice, so we know that the weight, f of g, is, what was it, 200 newtons. But the normal force is 300. The surface is pushing back with way more force than what the weight of the refrigerator is. Okay, so now this is unique because normally if a object was just sitting on a surface, the normal force would equal to the force of gravity. But in this case, the normal force, I'm going to put this up here, the normal force was so much greater than the force of gravity. And that's because this weight is pulling this object into the surface. And because this object is being shoved into the surface has to push up with more force than what it would normally do if it was just a weight. All right. I'll see you next time. Next video, we are going to be diving into the world of hanging signs. Bye-bye.